Okay. Okay, so I apologize. Today's not going to be the most entertaining day, but like I said, there is just some basic stuff we need to get set for where we're going over the next couple weeks. Before we can do anything today, we have to discuss a term that is new to you. It's more of a phenomenon than anything, and it's this thing that we call a concentration gradient. Okay, concentration gradient. Where have you seen this word before? Concentration. What?
Concentration camps.
Okay, concentration camps. Okay, where else? Yes. Any guesses of what it means?
I'm guessing if it's concentrated version of something like approaches and stuff where approaches like a bird.
Okay.
Concentration is focusing on one thing.
You're what?
Focusing on one point.
Okay, so it's not that concentration. It's not like I need to focus on this. Okay? Instead, what this concentration is all about is the amount of something. Okay? So what the concentration gradient is referring to is the difference in concentration or difference in the amount of something from one area to another. Okay? That's what that is referring to. Okay? This concentration gradient is something that exists in the world. It's a phenomenon that exists in every part of the world, the living things on the world, everything. Okay? What it really means is that things always want to go from a high concentration to low concentration. Okay? If there's anything that you get out of today, it is understanding what this thing is. Okay? Because everything in the natural world always wants to move from a high concentration to a low concentration. Okay, so let's kind of break that down for just a second. When we're looking at people right now in this room, is there a high concentration of people compared to the hallway, or is there a low concentration of people compared to the hallway? High. High in here, right? Okay? Now, I'm going to test my theory of whether the concentration gradient is real. How many of you want to leave? Right? So generally, you want to move from a high to low concentration, right? Okay? Here's a little better example. Okay? Kennedy offered up her perfume for us to do this demo today. Okay? So what I want to look at is this idea that things naturally always want to move from a high concentration to low concentration. Okay? So what I'm going to do is, over here with Kai, I'm going to just unload some perfume right here in this corner. Okay? Now, the perfume is going to be high in a high concentration where? Here or out there?
There.
Here. Okay? So if our theory is correct, should everybody be able to smell the perfume?
No. If you turn on the fan,
Okay, well I'm not going to turn on the fan. Well, you want me to close the window?
no.
Close the window.
Okay.
Okay, so no airflow. Let's see what happens. When you smell it, I want you to raise your hand. And if you need to drop your mask for just a little bit, you can.
Legal. I gotta do this.
You don't smell it yet over there.
No. Hi, you can smell something. I don't.
Don't smell it yet?
My senses are broken. Oh.
Smells sweet.
Yeah.
Cupcakes and rainbows.
Oh, it's not now.
Got it? It's going to take a minute to get to you.
I can't smell.
Why does it spray make you
I got your nose. Can't smell.
Kennedy, you got it yet?
If it's gonna go over there and you know it, you can like,
Okay, we'll give it, it's getting strong. We'll give it a minute. Okay, so, whew, it is strong right here. It's coming, watch out. It's coming to get you. Okay, so with the concentration gradient, what we should see and what we will see here in just a minute, it's going to take just a second, is everything wants to move from high to low concentrations. Okay? So from this corner, that perfume wanted to go from that large concentration and spread itself out to the lower concentration. Got it now? It's really strong right here. Okay? And so you see this in a lot of different things that you use all the time in your houses, right? Think about your little diffusers, right? Whether you plug it in the wall or whether it's one of those little jars of oil with sticks coming out. You know what I'm talking about? Okay? Those guys use the concentration gradient all the time. You have a large concentration of the smell in the little oil jar, and inevitably it's always going to travel out to the lower concentration, making your house or making your room smell good. Okay? That's what is, it's science, it's happening, right? So, concentration gradient always goes from high to low. Everybody got that? I'm going to say that 100 more times in this class because it's the one thing you need to get today. Okay? So, there's two phrases that we will use over the next couple weeks, and honestly maybe throughout the entire year, that we should understand. You are either going against the concentration gradient or you're going with the concentration gradient. If you're going with, that means it is moving from high to low. If you're going against, that means you're going low to high. Okay? Again, naturally things always want to go with. But there are some cases where things go against. For instance, if I wanted all of that perfume to go back over there, that would be against the concentration gradient. What would I have to do? I'm going to have to fan that bad boy, right? Like really, really, like a lot, okay? And I'm going to have to use a whole lot of energy to do that because it doesn't naturally want to move that way. It wants to move out into the lower concentrations. Does that make sense? Okay, so let's kind of apply that to biology and where this matters, okay? So specifically when we're looking at the cell and how things get in and out, there's going to be two types of transport, two types of movement and how things get in and out of cells. The first is what we call passive. What does that word mean?
Passive means like, only, there are two types of passive I know. One is that supervised and the other one that just goes naturally with the flow.
Okay, it just goes with the flow, right? If you're a passive person, you don't want to make anyone mad. You just gotta go with it, right? Passive transport goes with the concentration gradient. It's naturally going to move from high to low. Okay? So passive transport is always going to move with the concentration gradient. Now, does that happen naturally, or do you have to use energy to make it happen? What do you think? What?
Does not require energy.
It does not require energy. Because again, everything in the world naturally moves from high to low. Okay?
Not my stupidity.
Everything wants to move from high to low.
Not my stupidity.
No, it stays the same.
Okay? Now, there are several types of passive transport which we'll talk about over the next couple weeks or so. So today you don't need to write these down necessarily. I'm going to talk about them just for a second, just so you can recognize them. But again, you don't need to write all of this. Okay? So passive transport, there's three types that we have looked at and that we're going to look at. Okay? The first of which is what we call diffusion. Okay? I'm just going to skip here. Diffusion. So this is the example we just did with the perfume. Right? Particles or molecules want to move from high to low concentration, so they do. Okay? The perfume example. The plug it in your wall is an example. When someone over on this side of the room farts and the whole room can smell it, that's diffusion. Right? Okay? Those are all examples of diffusion. It's naturally moving from high to low by itself. Okay? The second type of passive transport that we'll look at is osmosis. Anybody know what that is? Heard of Osmosis Jones, that dumb movie that came out a long time ago? Okay? It's all about the movement of water, okay, from areas of high to low through a membrane. Okay, we're going to talk about that guy on Thursday in a lot more detail. Osmosis is all about water. And then the third type is one that we've already kind of looked at a little bit through our macromolecule stuff, and that is what we call facilitated diffusion. Anybody have any idea what facilitated means? It means to help. So it's the diffusion with help from proteins. Okay? So remember these guys? These guys?
Yes.
Okay, so we'll flip this that way. So these proteins here are what would be used for facilitated diffusion. Because normally with diffusion, things can move through the lipids, right? But if they're too big, they have to get help from the proteins, right? We talked about what molecule having to use proteins to move through something. What example did we give during our macromolecule stuff?
Water is in the chemical.
Carbohydrates, glucose, right? Glucose has to move through proteins, okay? So that would be an example of where you would have facilitated diffusion. Okay, so if it's not passive transport, what do you think the other one's called? Active. If it's not passive, it's active. Okay, remember, passive moved with the concentration gradient, and it did not require energy. Active transport moves against the concentration gradient, and it does require energy. Again, think about me trying to get all of the perfume to stay in that corner. What do I got to do? I got to fan it. Does that take energy? Yes. The perfume does not want to go that way. So if I want it to go against the concentration gradient, I got to put energy into it and make it happen. Okay? So active transport, two big ideas. It goes against the concentration gradient, which means it's going from low to high. And then to do that, you've got to have energy. Okay? Now look back at our little cell here. Okay, so active transport, there's a couple different ways, or a couple different types, but we're not going to talk about many of them. Okay, but what do you notice about these three proteins here that these two do not have? Gates. For those gates to move, do you think that requires energy?
Yes.
Yes. So these are generally going to be used in active transport. Okay, these are what you would call protein pumps, which pump things across going against the concentration gradient. Okay? Now, some of you, we talked about sugars and insulin and that kind of stuff, right? You remember that? For some of you? Okay? So sugar uses a protein that has gates, but it doesn't require energy. Instead, what molecule does it have to use to open it? Insulin, right? We didn't talk through that with everybody, so if that wasn't, you don't worry about it. Okay, everybody good? Does that make sense? Okay, so passive and active. Okay? It's all about the concentration gradient. Okay, time out. Quiz time. Ava,
Yeah.
things always want to move from what to what?
From high to low.
High to low. Good. Ty, concentration gradient moves from what to what? Concentration gradient moves from what concentration to what concentration? What did she just say?
Say the same question?
Yes.
Okay.
Same question. Maya, for something to move across a membrane without the use of energy, it's got to move from what concentration to what concentration? High to low. Remember, I said that's the one thing you need to know before you leave, because everything else makes sense with that. Okay, it's got to move from high to low. Okay? Greek. If something has to move low to high, what do you have to give it?
Energy.
Energy. Very good. Excellent. Okay, so we're going to come back to our example of Lake Nyos. Okay, so let me get rid of this. Everybody got your whiteboards on your table? Okay, on your whiteboard, I need you to draw a cell, just a big old circle.
I need a marker.
We had no markers. I need markers.
There should be markers around. If you have more than one marker, throw it at Greek. Greek, catch. Gannon, catch. Terrible catch. Didn't you yell at him? Kai. Need a marker? Okay, so on your whiteboard, draw a cell. Just a big old circle.
Circle?
Big old circle.
Okay.
How big?
Does it have-
Big.
Can it be an oval?
Sure.
Oh.
Yeah, that's a good circle. Look
Is
at
that
that.
big enough?
I'm retiring. I'm going to be a professional circle maker.
Oh, that's a good one.
Probably make one.
They have an app for that.
I have an app for that.
Yeah, so you can test.
Okay, in your circle, okay, this is our cell. In the cell, I want you to put, oh boy, that marker sucks.
My marker.
Buckets. Nope. So close. So close. Okay, we're gonna put three CO2s, and one O2. Just like that. And then outside of the cell, we're going to put three O2s and one CO2. So this is outside the cell. This is inside the cell. When I say outside the cell, where specifically would these CO2s and O2s be? In the bloodstream.
Yeah.
Very good. Okay, this is just a very simplistic model of this, right? Okay, so on your whiteboard, I need you to draw an arrow showing me which direction the oxygens are going to be moving. Will they be moving into the cell or out of the cell? Draw that right now. And you can just make one arrow. You don't have to show each.
Repeat that a little bit.
In the cell or out of the cell? Jenna, what do you think? Why? Don't overthink it. What have we been talking about for the last 20 minutes? Okay. Kennedy, help me out here. Outside of the cell, is there a higher concentration of oxygen or CO2? Okay, so oxygen is high out here. What about inside the cell? So oxygen concentration would be low in here. So Jenna, where is the oxygen going to move?
No.
It's going to go in because things always want to move from high to what? High to low. Right? The concentration gradient is high to low. Oxygen always wants to move from the high concentration to the low concentration of oxygen. Does that make sense? Okay? So leave all your oxygens and CO2s. Just erase your arrow. And I want you to draw another arrow showing me where your CO2 would be going, inside or out of the cell. Schmeaton, what is it?
I don't know what the question was.
The question was, where's the CO2 moving?
Oh, outside.
Outside. Why?
Comes in.
Why?
Because O2 comes in, CO2 goes out.
No.
It's carbon dioxide.
No. The high concentration of CO2 is in the cell, so therefore it's going to be moving out. Okay? All right, so walk you through something here real quick. Here's my lovely diagram. Can everybody see this? Okay, so, right here, by the way, how about this face? Pretty good, yeah? I was pretty impressed. Pretty impressed.
It's called an underbite.
So this guy, he's breathing, and he breathes in what? Oxygen. Oxygen goes to his lungs, it then gets dumped into the bloodstream. Okay, your bloodstream right now looks just like this. It is high in O2 and low in CO2. Why? Schmeaton, why?
What?
Why is your bloodstream high in CO2, or I'm sorry, high in O2? Why is it always loaded with oxygen? It's common sense. Why?
Suck it in.
Because you breathe it in all the time, right? You never stop breathing. You're always breathing, so therefore your blood is loaded with oxygen. Okay? Inside of your cell, your cell needs oxygen for what?
Energy.
For energy, right? Remember, we said oxygen and glucose go into the mitochondria to make energy, and what's the byproduct? What's created? CO2, carbon dioxide. So inside of your cell, what is there going to be a higher concentration of? CO2 or oxygen? CO2, because all the oxygen is getting used, right? So inside the cell, you have high CO2, low oxygen, right? Now, naturally, where is your oxygen going to want to move? Into the cell or out of the cell? Into the cell, okay? It moves into the cell so that you can create energy, right? Where does the CO2 want to travel? It want to move out of the cell into the bloodstream so that you can then do what? Breathe it out, right? Isn't that crazy? Like, this concentration gradient exists so that you can do things like this naturally. You don't have to force yourself to get oxygen. You don't have to force your cells to make energy. It just happens because these things naturally want to move from the high concentration to the low concentration. Make sense? Okay, so draw your cell again. Nope. Keep your cell. Erase everything in the cell. Okay, so in the cell, I want you to draw, what does your cells look like right now in relation to the concentration of CO2 and oxygen? Okay, so draw some CO2s, draw some oxygens inside and out of the cell. Show me what the situation that your cells are in right now looks like. Remember what we said naturally always is happening with CO2 and oxygen.
Very good. Very good.
Maybe trim it down a little bit. I'd say draw maybe 3 or 4 most. 3 or 4 molecules.
I'm reading really fast.
Okay, that's fine. Okay, so inside the cell, what should I have a higher concentration of?
O2. I mean, not O2, CO2.
CO2. Very good. Okay, outside of the cell, what should I have a higher concentration of?
O2.
Okay. Okay, so let's go back to the example of Lake Nyaris. Okay? So these guys get hit with this cloud of CO2. Okay? So what is going to be affected first, inside or outside of the cell? Okay, what's going to happen? What? Who said something over here?
I did.
What did you say? The O2 is not going to change, but you are breathing in more what? CO2. So we can just add some CO2. So now the concentration of CO2 outside of the cell in the bloodstream is really high, right? Okay? Inside the cell, is the oxygen still lower than outside? Yeah? So these oxygens are going to move in, right?
And then.
Okay? And then what happens to these oxygens?
Turn to CO2.
They turn to CO2.
Right, they make energy, which then produces CO2.
And then that CO2 comes back down.
So what's inevitably going to happen to this person?
Yeah.
Why?
Because there's too much carbon dioxide in the cells and there's nowhere for them to go.
Okay, there's a bigger reason. Yes, obviously there's a crap ton of CO2 inside of the cells, but why do they die?
Because they're not breathing in the oxygen and they don't get the oxygen out of their bloodstream, which means they're not getting energy and then they die.
Good. Inevitably, they're going to use all of the oxygen up that they have, right? They're going to use that by making energy, but when they make the energy, it's going to produce more CO2. Eventually, all they're going to have is CO2 on the outside, CO2 on the inside. Why is that a problem?
Because we need oxygen to produce energy, and without energy, our organs can't function.
If you can't produce energy, what does the cell do?
Die.
And if your cells die, what do?
You die.
You die, right? Okay, so in this case, in this example, okay, it shows the importance, obviously, why we need oxygen. Oxygen, we breathe it so that we can make energy, okay? And in these cases, all they're breathing in is CO2. If all they breathe in is CO2, all the oxygen is going to move in and get used, and then they're just crap out of luck, right? Then they can't make any energy and they're going to die, okay? So the easy answer that most of you answered on Monday was they suffocated. But technically they didn't. Technically they died because they couldn't produce energy. Okay? So, couple questions, and then we're done. Who wants them? You gotta get 3 questions right.
Who wants to be a millionaire?
Yeah, 3 gets question 1. Brayden, you get question 2.
Jackson, number 3.
Who's not making eye contact?
I'm putting the dinosaur
All right,
back.
Jackson, you got question 3. Okay, so question number 1 is, Guri, CO2 and oxygen move in and out of the cell using what form of transport?
Howdy, pardon.
We talked about 2 types of transport today.
Oxygen.
Nope. We talked about passive and active. Passive, thumbs up if you agree. Thumbs down if you don't agree. Both hands in the air if you just don't care right now.
Roller coaster.
Thumbs up if you agree that this is passive transport. Oxygen and CO2 moving in and out of the cell is passive transport. Thumbs up and thumbs down. Show me, everybody.
Woo.
Everybody, up or down, up or down, up or down, up or down. Ava, up or down. Yeah, okay, good, great. Question number 2. What type of passive transport is occurring between CO2 and oxygen? Diffusion. Very good. Diffusion. And then last question, Jackson. Diffusion, specifically with CO2 and O2, it moves with or against the concentration gradient, which means it's traveling from what to what? High to low. Everybody good with that?
Yep.
Okay, do me a favor. Erase your boards.
No.
The markers, I need to end up on one of my whiteboards somewhere. The erasers and rags need to go in here. And then bring your whiteboards and put them up here. And then you are free to scan.
Scatter.
Oh my God, the person just died. You know, he just
And make sure you thank Kennedy for making my room smell pretty today.
What are you gonna do? Mr. Gollum, do you have another class in here?
What?
You can have another class in here?
Nope.
Good.